When you think of science, what comes to mind? Maybe a lab coat-wearing genius carefully mixing chemicals, or maybe you picture a list of steps: observe, hypothesize, experiment, analyze, and conclude. That's the scientific method, right? Well, kind of. What is the scientific method? The scientific method is often taught as a neat checklist, a one-size-fits-all recipe for discovery. It became popular during the 17th century when thinkers like Francis Bacon emphasized observation and experimentation to uncover nature's secrets. The basic steps look something like this. 1. Observe something. 2. Come up with a hypothesis to explain it. 3. Test your hypothesis with experiments. 4. Analyze the results. 5. Decide if you were right or start over. Sounds great in theory, but reality
is far messier.
The reality of scientific practice, scientists don't always follow these steps in order or at all. Some discoveries, like X-rays or penicillin, were made entirely by accident. And in fields like astrophysics or climate science, controlled experiments aren't always possible. Instead, scientists rely on models, simulations, and data analysis. The scientific method, then, isn't a rigid formula. It's more like a set of guiding principles that adapt to the needs of different disciplines. Philosophical perspectives, philosophers of science have challenged the idea of a single scientific method for decades. Karl Popper argued that real science isn't about proving theories, but falsifying them, trying to show they're wrong. Why? Because a theory that can't be tested or disproven isn't scientific. For example, the Earth revolves around the Sun is falsifiable because it can be tested. But invisible fairies control gravity. Not so much. Thomas Kuhn introduced the idea of paradigm shifts. He said science doesn't just march forward, it occasionally flips the script. For example, the switch from the geocentric Earth-centered model of the universe to the heliocentric Sun-centered one wasn't gradual, it was revolutionary. Kuhn's point: science is shaped by the dominant ideas of its time, and when those ideas are overturned, everything changes. Paul Feyerabend took things even further. In his book Against Method, he claimed anything goes. His argument wasn't that science should be chaotic, but that rigid rules can sometimes stifle creativity. Think of breakthroughs that came from bending or breaking the rules. So, what's the takeaway? The scientific method isn't wrong, it's just oversimplified. Science thrives on flexibility, creativity, and questioning assumptions. By understanding the complexities and philosophical underpinnings of science, we can better appreciate its achievements and its limitations. Next time, we'll dive into the role of evidence in science, how it's gathered, interpreted, and used to shape our understanding of the world.